Hello everyone, good evening. My name is Imran Hussain. So I'm presenting the machine learning framework for coefficient adaptation in Liutex based subgrid model for large eddy simulation. So here is our outline of the presentation. I will talk about little bit about numerical and computational method first, and then I'll go over the subgrid models and our proposed method to machine learning framework to adapt coefficient in Liutex based subgrid model. And I'll show about our machine learning model architecture, implementation process, and case study with the result finding. So here is our turbulence modeling and computational methods are the direct numerical simulation DNS, Reynolds average neighbor-stokes RANS, and large eddy simulation LES. So DNS solves all scales of turbulent motion directly without turbulence model. And neighbor equation discretize in time and space to solve numerically. And again, in DNS, you can see resolves the largest to smallest scale of turbulent motion. However, in DNS, the computational cost is very expensive. So RANs are the time average equation of motion for fluid flows. And in an instantaneous quantity is decomposed into its time average and fluctuating quantities. So RANS does not resolve turbulence directly. It models the effect of turbulence using extra terms like Reynolds stresses and its turbulence model, for example, K epsilon, K omega models. And RANS is much cheaper and faster than DNS or LES, making it ideal for industrial application. And so it is less accuracy in highly separated flows, vortex dominated flows, and flows with strong unsteadiness. So large eddy simulation LES is simulate large eddy or vortex structure directly and uses subgrid models for filtered small scale eddies. And in LES significantly reduces computational cost compared to DNS while still preserving the turbulent flow and offer better accuracy compared to Reynolds average neighbor-stokes equation. So in LES applies a special filtering operation to the neighbor-stokes equation to separate the large scale and small scale motion. So filtering presents an unknown residual stress which is subgrid scale and which need to be modeled, and the largest scales or eddies resolved numerically. So next our talk is about the subgrid scale model, and this is the subgrid model defined by the formula tau ij minus 1/3 tau ij delta ij equal -2 nu t s ij, where 1/3 tau ij delta ij is the isotropic part in subgrid stress tensor, and delta ij is the Kronecker delta function, and Sij bar is the state rate of tensor. And so these are very common and very popular subgrid scale model. These are some Smagorowski model, Weyl model, Liutex based model, and K equation model, dynamic coefficient adaptation, which is called dynamic Smagorowski model. So most of the model are based on the constant coefficient based model, especially in Smagorowski, Weyl, and Liutex are based Liutex based subgrid model. And K equation is in the default subgrid model for open form. And then dynamic coefficient or Smagorowski model, dynamic Smagorowski model is not based on the constant coefficient based, which is dynamic coefficient adaptation based. And for our method of the research is we are same things doing as dynamically coefficient adaptation by Liutex based coefficient model, but not by adapted the coefficient using the machine learning model using DNS data. So here is the formula for the Smagorowski model, and I have seen a lot of speakers already talked about these models. So in Smagorowski model use that the constant coefficient, And you can see there are a lot of drawbacks in Smagorski models, which overestimates the eddy viscosity under a strong background shear, and it leads to a non-zero residual viscosity and shear stress near the wall. And then the wall adapting local eddy viscosity model improved the Smagorski model, but still in that wall adapting local eddy viscosity model, they applied the constant base coefficient, and you can see that the keep the coefficient CW is 0.325. So in well model improves the prediction of subgrid scale turbulence, particularly in wall-bounded flows, and resolving the near wall region can be computationally expensive. So dynamic Smagorski model is not in constant base coefficient model, but it is specially bearing and used to test filter to delta, and that coefficient defined by C equal to Lm over mm, as Lm is Germano identity tensor and Mij is model tensor. So before going to our Liutex based subgrid model, I'm just going over the Liutex. So Liutex is a third generation vortex identification method defined as R equal to RR. Here small r bar is the eigenvector of the velocity gradient tensor, and now we have vorticity omega dot r greater than 0. As for strength, an explicit formula is found by Wang in 2019. He defined r equal omega dot r minus root square omega dot r square minus 4 lambda c square, where omega is vorticity, r is Liutex direction, and lambda ci is the imaginary part of eigenvalue of velocity gradient tensor. So merit of Liutex, which is physical meanings is clear. Direction is vortex axis, and magnitude is twice angular speed. And in Liutex, which is not contaminated by shear or stretching. So this is our Liutex based model. Is the model defined by Ding Wang in 2022. The formula is nu t equals C nu delta square r. So where C nu is a coefficient and delta is the filtering length scale, and r is the Liutex magnitude, which is defined as also r bar equal root square r1 square r2 square r3 square. These all r1, r2, r3 are Liutex components, and this new coefficient given as constant 0.032. So for our proposed machine learning model is based on coefficient machine learning based coefficient adaptation is nu t equal C nu ml delta square r, where C nu ml equal we find the function of local flow features. So that function of local flow feature we find from the neural network or machine learning model. So the local flow features are extracted from the DNS data. So here, this way you can find machine learning coefficient adaptation like C mu ml equal. For this work, I used PINS model. PINS is a physics informed neural network, and we've extracted the feature from the DNS data. The data are the R1, R2, R3, R bar, S bar, omega. These all features we've extracted from the DNS data. And according to this DNS, this data, the machine learning or the PINS model predicted the C nu or coefficient. And we use the training data as DNS backstep flow, where Reynolds number are 22,000, and real time prediction we given 169,000 cells per time step. So a little, fundamental of basic neural networks. According to our work, we have a neural network mimics how our brain processes information. So in neural network architecture, we have first input layers, and then hidden layers, and then we find the output layers. So for our case, in inputs, we have flow features. These flow features we have extracted from the DNS data. In the processing, hidden layers processed according to the data, and it's learn the patterns. Then in output layers, we can find whatever we given that, like according to our like model or our desired work. So for our case, we are getting the CNU, the model coefficient. So our pin architecture, we use that the input layers, and we just started with just few hidden layers. The first hidden layer have 64 neurons. Second hidden layers have 64 neuroseconds, and third hidden layers 32 neurons. And in output layers, we have CNU ML. So that methodology we have methodology we have in our machine learning CF integration. So from that physics informed neural network architecture, we have that, and we extracted the feature, and then pin inference. The pin inference we used first that the pin model in the Python, and over there we use that ONNX runtime. So ONNX runtime, which is like a machine learning inference, like we can change the program language to the different solver. So the basically we work on that the simulation in the open form solver. So separately, I work on that the ONNX runtimes or pins model in the Python based. Then we can implement it into the OpenFOAM. And OpenFOAM, you know all that, which is based on the C++ language. So the SGS computation we have applied especially varying CNU ML to Liutex based eddy viscosity. So that definition we have find using our that model. So the implementation and success, since it is very primary process of the machine learning based model to the Liutex based subgrid model. First, we try to implement if the machine learning model works on that, and if we find the different CNU or different coefficient instead of the constant based CNU. So we are able to make an infrastructure of ONNX runtime, which is compiled in the OpenFOAM as well. And then we have custom Liutex ML model, and this is also compiled in the OpenFOAM version 2312, and parallel execution also applied. And so these all runtime performance we have. Real-time inference we have 60K per time step, and specialty varying CNU ML field that we find from the DNS data, and dynamic coefficient updates. So according to our time step and according to our case, we can get dynamic coefficients. And so this feature extraction we have from the DNS. So for validation of our model, I choose that step flow. So we going through that PITJLE backward step flow, and also the recent study of Park PITJLE case. So backstep flow is it is a sudden geometric change. The flow when sudden geometric change, and it pressure gradient also exists, and it creates some primary and secondary vortex. So this is in general case for the PITJLE geometry. So, but we went through in our in recent study of the Park PITJLE case. So we use very similar of the case studies like geometry, but different domain. And so we have step height h is equal to 0.0254 meter, expansion ratio 2 and 1. So wood span 0.173 meter. Reynolds is 22,000, and total cells for the course grid 169K. So mesh type is structured hexahedral mesh, and refinement near step and wall. So in the result section, we figure out that our machine learning based Liutex subgrid model given exact like a backstep flow structure. Here we have seen that we have two vortex generated, the primary vortex and secondary vortex. Also, we have find time average E velocity profile in the center plane for Reynolds number 22,000, and we compared with the DNS results and the Liutex, our Liutex based model, and the Liutex ML, the current study. So for Liutex ML based, we couldn't go over a good time step because this one we run over in our local computer, but still in the parallel computing. So we couldn't go over in like HPC system over a large time step. So still you can see that in Liutex ML method is very close to the Liutex based like constant based model. And in some part we can see in the near the wall, and even the Liutex ML based model is better than given better results than the Liutex constant based model, and which is very close to the DNS. Also, we check RMS profile, velocity profile. We find very similar results, and we can see that most of times the Liutex ML and Liutex constant based model given very similar output, and so here is our main goal is to find like the coefficients adaptation in the different cell. So from this figure we can see that we have in the C nu or coefficient in different coefficients, not in the constant based. So though it is very large coefficient right now, but we are keep working on it to develop in different varying like machine learning model. So here you can see that the C nu is like we have highest C nu is 0.09 like coefficient, and it is varying in local flow. It's not in constant based. So that was actually our main goals, to find the C nu in local flow specialty according to the DNS data. So we can find also in open form given us that different C nu field, not in one constant based C nu. So conclusion and impact. First of all, we completed spin and then ONX and open form. We compiled pins and open ONX. These all models into the open form, and we find this also the technical achievement is that the real-time machine learning inference integrated in the open form CFD solver, and we have especially varying coefficient from flow physics. So research insight is if you see that DNS and LES scale separation is critical. So sometimes geometry matching is in training data matters. So machine learning models are resolution specific. So subgrid scale coefficient adaptation by machine learning. So we have infrastructure ready, which are the open form integration. So ONNX runtime integration and parallel execution as well. So the work on progress and future work, we have retrain on LES resolution datasets and validate with different computational domain with geometry. So we'll develop machine learning method that can do simulation for all case studies. We'll apply adjoint based model for coefficient optimization. So we'll work on advanced machine learning methods such as reinforcement learning, uncertainty quantification, and surrogate model to develop best machine learning based subgrid scale model, which incorporate to large eddy simulation. So thank you. That's all my presentation, and here's the references. And if you have any question, you can ask me.